Okay, let's go ahead and get started. So first, just administrative announcement. I've decided that there won't be a problem set due next week. It's the middle of the semester. We missed one class this week anyway. Everyone's probably busy with other things. So, don't ever say I never did anything for you, okay? So no problem set due next Friday. If you need an extra few days on the problem set this week, that would be fine as well, okay? Maybe just if you're going to turn it in later than Monday or Tuesday, maybe if you wanted to do it, say Monday, that would be just fine. Okay. So no problem set for next week. Okay. So today what I want to do is finish up with our discussion of Feynman diagrams and in particular discuss a few of the features of Feynman diagrams and scattering amplitudes in momentum space. So far, our discussion has mostly been restricted to Feynman diagrams in position space, where one computes the expectation values of various observables, such as time-ordered products of field operators. But if we're interested in performing, say, a scattering experiment, as seen in an accelerator or something like that, then we really need to understand the Feynman diagrams in momentum space. And in particular, what we are doing is we are interested in computing things like the overlap or the amplitude for some initial set of states involving some particles labeled by their momenta, let's say k1 up to kn. You want the amplitude for that to evolve into a final state involving particles, say, with momenta k n plus 1 up to km. Okay. And previously, we worked out using the LSZ formula, which related position space expectation values to these scattering amplitudes. We worked out the Feynman rules that one would use for calculating in momentum space. And what I'd like to do today is first review for you very briefly how these Feynman rules work, and then use them to calculate a few quantities of interest, and begin our discussion where we'll try and make contact between these sort of formal developments in Feynman diagrams and the more practical things such as scattering cross-sections that you might observe in a laboratory as the outcome of some scattering experiment. Okay. So let me just remind you of these Feynman rules in momentum space. So in general, we know that this S-matrix element, or this scattering amplitude, should take the form, so first of all, there should be a momentum-conserving delta function, which just states that momentum is conserved. So the delta function should be the difference of the sum of the incoming momenta and the outgoing for momenta, times some quantity, which is usually denoted m, where m stands for matrix element. And this m is computed using the momentum space Feynman rules, which I will just remind you of, although we worked them out about a week and a half ago or 2 weeks ago when we discussed the derivation of the Feynman diagrams using the Schwinger-Dyson formalism. Now, having rederived these Feynman rules using the path integral formalism, we'll be able to understand a little bit better exactly which Feynman diagrams will end up computing to things like scattering amplitudes. So just to remind you, if you're studying a scattering process where you have some ingoing particles and some outgoing particles, then you start by drawing external lines for each ingoing and outgoing particle. Okay. And then you connect the lines in all possible topologically distinct ways using the interaction vertices. So, for example, in a phi cubed theory, the interaction vertex would be a trivalent vertex like this. In a phi fourth theory, there would be a quartic vertex. Or in a theory with interactions between different particles, there would be different sorts of interaction vertices that would allow, say, two particles to combine to form a third particle of a different type. And you join up these interaction vertices using some number of internal propagators, which are represented by lines. And then, to keep track of the momenta, we'll just draw arrows on each line to keep track of which direction the momentum is flowing in this Feynman diagram. And the convention that we'll stick to, and this is really just a convention, is that incoming external particles have arrows that point in towards the center of the Feynman diagram, that is to say, towards the first interaction vertex. Outgoing or final state particles have outgoing arrows. And internal lines, well, it's arbitrary. You can just draw them however you like. So you construct a Feynman diagram, you sum over all possible topologies of the ways that you can connect these external lines using interaction vertices and propagators. And then you label each line by the momentum of the particle which propagates along this line. And you enforce momentum conservation at each vertex. So, for example, if you have an interaction vertex that looks like this, then to enforce momentum conservation, if you know two of the momenta, let's say that this first one is p and the second one is k, then this lower one has to be p minus k. Okay. The minus sign comes because you think about momentum flowing along the directions of these arrows. This arrow here points the same direction as this arrow here, so that's why you have a plus p in that p minus k. And because these guys have it has different directions from the k over here, you get a minus k. Okay. Or, for example, in a trivalent vertex like this, if you labeled the momenta differently, here you would have pk, and there you would have p plus k. Okay. And now that you have this Feynman diagram, which has been marked up by the various momenta, you just use the Feynman rules to write down the value, the contribution of this Feynman diagram to a scattering amplitude, using the rule that each internal propagator, labeled by a momentum p, will be equal to I over p squared minus m squared plus I epsilon. Each of the interaction vertices, just as they are in position space, will give you a factor of the coupling constant. And each one of the external legs, well, that just gives you 1. The reason why it doesn't give you a factor of 1 over, or I over p squared minus m squared, is that in the LSZ formula, when you turn the time-ordered expectation values into scattering amplitudes, you have that factor of the Klein-Gordon operator d squared minus m squared that's multiplying the Feynman diagram, which precisely cancels that pole. Okay. So this was part of our derivation of these Feynman's momentum space Feynman rules about 2 weeks ago. Okay. Okay. So now you have this formula, but just enforcing momentum conservation will not completely fix all of the momenta that are internal to your diagram. And in particular, for an L-loop diagram, that is to say, a diagram with L internal loops, you will be left with L undetermined momenta. And then you just integrate over them. Okay. So for each of the momenta, you'll just integrate using the standard measure factor, so where we divide by some 2 pi to the 4th. So that's just some standard convention. And the thing to notice about this is that these internal particles do not have to have the property that their momenta is equal to the mass squared. So for a solution to the equations of motion, a plane wave solution, k squared is equal to m squared. That's the equation of motion. Okay. But the internal particles do not have to obey the equations of motion. So that's the statement that these virtual particles, the ones that appear only as intermediate contributions in a Feynman diagram, don't have to be so-called on-shell. Okay. Where on-shell is just a fancy way of saying that something is on-shell if it solves the equations of motion and off-shell if it does not. Okay. Shell here refers to the fact that in momentum space, k squared equals m squared would be some sort of spherical shell in momentum space. Okay. And then that gives you the answer. All we have to do then is divide by an appropriate symmetry factor. And as in the case of Feynman rules in position space, the number of symmetries is a diagram is the number of invariances of the diagram when you interchange propagators and vertices. Okay. So you divide by the number of symmetries under the interchange of the various internal propagators and vertices. And finally, as we saw last class, there are 2 further simplifications that we can use that would allow us to immediately discard some number of Feynman diagrams. In particular, you don't have to include any bubble diagrams. That is to say, we don't include any diagrams which have a piece that is completely disconnected from any external legs. And there were no bubble diagrams just because any bubble diagram contributed to the norm of the vacuum state. And at the end of the day, you're only interested in computing probabilities where you divide out by the norm of the vacuum state. You keep the vacuum state normalized. And we saw last class, last Thursday, that that magically cancels out all of the bubble diagrams. This was this business where we saw that the sum of all disconnected diagrams was the exponential of the sum of all connected diagrams. And the whole point of normalizing everything was just to remove, subtract out all of the bubble diagrams. And likewise, there are no tadpole diagrams. That is to say, no diagrams which become disconnected if you just cut one line. And that was because we always use this counter term. That is to say, we always shift the value of phi so that the vacuum expectation value of phi is equal to 0. If we were working in a setup where we chose not to remove this vacuum expectation value of phi, then you would have to include tadpole diagrams. Okay. And there are some cases where you may be interested in doing this. So for example, in any setup where the value of the scalar field would be some classical dynamical variable, so in the theory of inflation, for example, the value of the inflaton, which is the field that drives inflation, changes in time. And so if you set phi equals to 0 at some initial time, then at some later time it'll be non-zero, then you would have to include the appropriate diagrams that would come from the fact that at later times the vacuum expectation value of phi would be non-zero. Fortunately, in this class, we're in Minkowski space, no inflation required. So for the purposes of this class, we'll be throwing away all the tadpole diagrams, unless we get bored sometime in the next second semester. Okay. So there's a couple points that I want to make about these, and essentially all I'm going to be doing today is developing these Feynman rules a little bit more explicitly and discussing some of their implications. So the first point that I want to make is that these rules allow for both connected and disconnected diagrams. So, for example, let's say that we're interested in studying the scattering of, say, 2 particles into 6 particles in this phi cubed theory. Then one of the contributions that you might get might look like this. Okay, so these are your incoming particles, and here are your outgoing particles. But another contribution you might get would just look like this. So 2 disconnected diagrams. And usually, so first of all, as you can probably tell by looking at these diagrams, in the first case you have a genuine 2 to 6 point scattering, which can't be viewed as the composition of some lower point scatterings. But in the second case, all you really have is 2 cases where you have 1 particle decaying into 2. Okay. I'm sorry, what did I say 2 to 6? I meant 2 to 4. Okay. Sorry, my addition skills are really not on point today. Okay. So in the first case, you have some genuine 2 to 4 particle scattering, and in the second case, you really have just 2 instances of 1 particle decaying into 2. Okay. And the basic point is that you can always, whenever you have a disconnected Feynman diagram, you could always just interpret that as 2 separate processes that are happening that don't interfere with one another. So usually, we will always restrict our attention to connected diagrams. If you're interested in the contribution of this disconnected diagram to 2 to 4 particle scattering, well, then you really should just study 1 to 2 particle scattering and include the contribution of that twice. And in fact, there's one point that I would like to make, which is that there's a sense in which the contribution of disconnected diagrams to a given scattering process is always infinitely greater than the contribution of the connected diagrams to a scattering process. So in particular, if you look, say, at the contribution coming from some disconnected diagram to a scattering process, then you'll actually get 2 momentum-conserving delta functions. because it's the product of two connected diagrams. So, for example, in this case up above, if this was K1, K2, and K3, and here you had K4, K5, and K6, then you would have two delta functions, one which sets K1 to K2 plus K3, and another of which that sets K4 to K5 plus K6. Whereas the contribution from the connected diagram will always go like K1 plus K4 minus K2 plus K3 plus K5 plus K6. Okay. So you can see that if you put all of these, if you just enforce momentum conservation, then the first of those has two delta functions, whereas the second only has one. So there's a sense in which connected diagrams are infinitely suppressed relative to disconnected diagrams. So in the process of 2 to 4 scattering, if 1 to 2 scattering is allowed, that will always be the dominant contribution. So this is maybe a good time just to mention that this is related actually to a very deep principle in quantum field theory that's referred to as the principle of cluster decomposition. So the cluster decomposition principle is really one of those kind of deep subjects that normal classes in quantum field theory don't really touch on. Okay, we're not really going to touch on it either. I just want to state it for you because it's something that you may hear alluded to or referred to in discussions of quantum field theory. And the cluster decomposition principle is the following. Okay. The cluster decomposition principle is most easily understood if you think about particles in position space. So let's imagine that you're computing some expectation value of a bunch of field operators at positions x1 up to xn plus m. And let's imagine that all of the x1s up to xn's are close together. So this will be x1 up to xn. And the xn plus 1s up to xn plus m's are all close together. But this first set of x's is widely separated from the second set of x's. So there's some long distance between them. Or there could also be some long time. Okay. So for example, x1 up to xn could describe some scattering experiment that was done in the 1950s, and xn plus 1 up to xn plus m is some scattering experiment that was done yesterday at CERN. Okay, sorry, the LHC is off. No, it's on. It's back on. No, it's off. Anyway, these could be widely separated in space or in time, and the cluster decomposition principle is simply that the expectation values will factorize in the limit where the two sets of particles are widely separated. Okay. And you can see, so one thing that you can fairly easily convince yourself of is that this is true if the expectation values are computed using a local field theory. So in particular, if the phi's here are the fields and of some local quantum field theory, and these expectation values are computed using, say, the Schwinger-Dyson equations or the Feynman diagram expansion, then you can easily convince yourself that this is true. Okay? Because, as you saw in one of your problem sets last week, all of the various propagators that go into calculating these contributions to these expectation values fall off like 1 over distance squared. Okay? So there's very long distance separating these things. Well, they fall off like 1 over distance squared for massless particles, exponentially in distance for massive particles. In any case, they fall off sufficiently rapidly that this cluster decomposition principle is true. Okay? And so, in general, however, it's actually one of these deep and sort of unresolved puzzles in the subject of particle physics, whether the converse is true. Namely, if you assume the cluster decomposition principle, whether that necessarily leads you to a local field theory. Okay? So for example, if you assume the existence of some observables phi that obey this cluster decomposition principle, then that does that necessarily mean that phi comes from the quantization of some local field? Okay? That's unknown. So nobody knows the answer to this. People who try and delve into the foundations of quantum field theory often, instead of calling the cluster decomposition principle a principle, they'll call it an axiom. It's really one of the basic axioms of quantum field theory. It says that if you do a particle physics experiment in Alpha Centauri, then it will have very little influence on the particle experiments here on Earth, okay? Which is really unfortunate if you want to talk to people in Alpha Centauri. Okay, so as you can see, so I don't plan on talking any more about the cluster decomposition principle, but I thought that, at least in the context of thinking about connected versus disconnected Feynman diagrams, it would be worth mentioning. Okay, so at the end of the day, we are left with this set of Feynman rules. Okay, I guess it took more than a page, but we're left with this set of Feynman rules. We discard all of the bubble diagrams, all of the tadpole diagrams, and we focus only on connected diagrams. And what I'd like to start doing now is I'd actually like starting to compute some of these things, discussing their interpretation, and discussing what their actual practical implications would be for some particle physics experiments. Maybe before I do so, I should pause and see if there are any questions. Okay. Yes?
For the distance, you are considering that the space-time interval, the modulus is higher. So you say a long distance, but
yes.
Can be time and
it could be time, yeah.
And space. So
yes. So if the invariant, so when I say distance, I really mean invariant interval. Okay. So for example, let's consider the following experiment. Let's say that you're on Alpha Centauri and you create a photon and you send it to Earth. Okay. Then I have a particle detector here which detects photons by interacting with them. Okay. Then of course that will not give you a vanishing, the expectation value, the correlation function will not vanish. And it will not vanish precisely because that photon is traveling along some null curve, along a path where the invariant interval is equal to 0. Because it's traveling at the speed of light. On the other hand, if you tried to send a massive particle, then it would actually decay exponentially. Yes, good point, yes. When I say distance, I really mean invariant interval in the sense of special relativity. Good. Another question?
So we can prove this formula strictly by mathematics?
Well, you can, if you start with local quantum field theory, where these expectation values are computed using the sort of setup of Feynman diagrams and so forth, this is fairly straightforward to prove. Okay. What one cannot do is prove that, well, let's put it this way. You could either start with local quantum field theory and prove cluster decomposition. It's widely believed that you should be able to start with the principle of cluster decomposition, and then from that learn that particle physics must be formulated in terms of fields that fluctuate according to some action principle, but that's not known. Okay.
So this could also include the fact that we are in the closed space-time for this?
Absolutely, yeah.
So
Yeah.
plays a role that we are in.
Yeah, I mean, when I say distance, I mean Minkowski distance. Okay. Presumably there's some other version of cluster decomposition that you could work out in other spacetimes, but yeah. Yeah. So here I'm just focusing on Minkowski space. Yes?
What about entangled particles?
What about?
Entangled particles?
Yes. So of course, yeah. Now one needs to be careful when one talks about entangled particles, because in that case, yeah, I should be careful about exactly what assumptions I'm making here. So I'm assuming that I'm working in a vacuum state where there are no entangled particles. So that's actually a great question. So you can violate cluster decomposition if, for example, you work in a state where there are entangled particles. If I start with an entangled EPR pair, say, and I hand one to a friend that goes off to Alpha Centauri, then the results of our measurements will be correlated. Okay. So I'm implicitly assuming that I'm working in a state where in a vacuum state where there are no entangled particles. There are a variety of ways that you could do things that would get around cluster decomposition. So for example, if you work in a theory where there's not a unique vacuum state, then that will also violate the cluster decomposition. Good question.
But with the entanglement is considered local quantum field with
Yeah, so you can certainly construct entangled states in local quantum field theory. Okay. So for example, we haven't talked about we haven't talked about particles with spin yet, but you could imagine that you have some particle that decays into two other particles, and if those other particles carry spin, let's say this is S1 and S2 is the spin of those particles, then those spins will be entangled in general. Quantum field theory is a quantum mechanical theory. It has all of the properties of quantum mechanics. It's like quantum mechanics but better. So if there's entanglement in quantum mechanics, there's entanglement in quantum field theory. Good. Important point. Yes.
So can we interpret the result as a known result in statistics, that we have expectation value of some random variable and it's the product of the amplitude, for example?
Like the law of large numbers?
Yeah.
I would not speculate. Yeah, I personally don't. Yeah, okay. You could, yeah. I mean, yeah. I mean, certainly in yeah. Okay, so it's certainly tempting. Yeah, there's certain cases where statistical variables will obey very similar factorization properties. If you have some Gaussian spectrum of Gaussian fluctuations of some random variable that fall off with distance, then that's a quantum field theory, basically. And it'll obey the same cluster decomposition property. Okay. Yeah. You want to be careful about making too many analogies, but as I guess I probably alluded to a couple times before, there are very close analogies between statistical mechanics and quantum field theory. And sometimes they're not just analogies, but equivalences. Okay. For example, the reason why I always call the generating function a partition function by accident is that it's the partition function of statistical field theory. Okay. Good. So this really wraps up the portion of this course that's devoted to the study, the sort of systematic development of perturbative techniques in quantum field theory. And what I'd like to do now is just begin applying this to start understanding basics of scattering processes. First, just some formal properties today, and then moving on in the next few weeks to develop the basic scattering processes of quantum electrodynamics, which is sort of the best studied and most well understood and probably most useful, most famous quantum field theory. Okay. So what I'd like to do is I'd like to begin by just discussing the simplest type of scattering process, where you have two particles that are scattering off of one another. Okay, it might be the next to simplest process. The simplest, well, it might be the next to simplest process. The simplest process would be 1-to-1, which is, a little trivial. The next simplest would be 1-to-2, which would be some decay process. Today, I'd like to just start by talking about 2-to-2 scattering, because that's that's going to be our primary subject of interest typically when we talk about particle physics applications. So let's just begin by thinking about two incoming particles with momenta k1 and k2, which will scatter off of each other via some complicated process into particles with momentum k3 and k4. Now, as I said earlier, I'm only going to focus on the connected diagrams. Of course, there are disconnected diagrams where k1 just goes to k3 and k2 to k4, or k1 to k4 and k2 to k3. But if one is only interested in connected diagrams, then you can see that at leading order, that is to say, at order quadratic in the coupling, there are going to be three diagrams that contribute. Okay. So there's one diagram that looks like this, where k1 and k2 come together to form a second particle with momentum k1 plus k2, and then that particle subsequently decays to the particles with momentum k3 and k4. And here I've determined the momentum of that intermediate particle as k1 plus k2 by momentum conservation. But of course, that also has to be equal to k3 plus k4 by the conservation of total momentum. And so you could see, you could either use momentum conservation at that vertex to write it as k1 plus k2, or momentum conservation at that vertex to write it as k3 plus k4. And the fact that those two things are equal is just the total conservation of momentum. Okay. And there are two other very similar processes. So there's a second process where the particle with momentum k1, sorry, I'm not very good at drawing these Feynman diagrams using this tablet, where the particle with momentum k1 emits a second particle that is then absorbed by the particle with momentum k2. So in this Feynman diagram would describe a process where the particle moving on the top will exchange another particle with the particle on the bottom, and that intermediate particle will have momentum k1 minus k3, which is the same as k4 minus k2. Okay. And there's a third process, which is again an exchange process, except now the particle with momentum k1 is not the same as the particle with momentum k3, but rather is the same as the particle with momentum k4. Okay. And the particle with momentum k2 is the same as the particle with momentum k3. Okay. And you can see here I've drawn that little circle here to denote that one of those two Feynman diagrams don't cross, but rather one of them hops over the other. Okay. There's no rule that says all Feynman diagrams can be drawn on a two-dimensional piece of paper without crossing. So you should really think about those Feynman diagrams in 3 dimensions. And in this case, the internal particle has momentum k1 minus k4, which is, of course, the same as k3 minus k2. And so the contribution of these 3 diagrams to this scattering process will be the sum of three terms. So you get 2 powers of I times g, along with a power of I for each one of those internal propagators. And so you get 1 over k1 plus k2 squared minus m squared, plus the analogous terms coming from the other 2 processes. Okay. And all of these k's are momenta of external particles. So they are all on shell in the sense that they satisfy the equations of motion. So k squared is equal to m squared. And as I mentioned, these three diagrams have different interpretations. So the first diagram is interpreted as a process where two particles decay into a third particle. They combine to form a third particle, which then decays to form the final end state. Whereas the other two diagrams describe the exchange of an intermediate particle. And the interesting point and the important point is that the scattering amplitude has a pole when the internal particle is on shell. That is to say, it has a pole when K1 plus K2 squared is equal to m squared, or K1 minus K3 squared is equal to m squared, or K1 minus K4 squared is equal to m squared. And when we think about particle physics experiments, this is the primary signature for some new sort of particle. Okay? If your scattering amplitude, say for 2 to 2 scattering, has a pole, then you interpret that as some new particle that's propagating in some intermediate state. For example, so it's very often the case that you can't observe new particles directly. Let's say your detectors might not be built to detect whatever charge this new particle carries, but you can still observe it through poles as it propagates in some intermediate state. So when we study the properties of two-particle to two-particle scattering, it's important to notice that many of these degrees of freedom on which this amplitude depends are in fact completely fixed by the principles of momentum conservation and energy conservation. Okay. You might naively think that this amplitude would be some complicated function of K1, K2, K3, and K4. So K1, K2, K3, and K4 contain together 12 degrees of freedom. Well, they really contain 16 degrees of freedom because each K has 4 components. But 4 of those are removed by the condition that these Ks are on shell. So that leaves you with 12 degrees of freedom. And you might think that these amplitudes would be some complicated function of these 12 degrees of freedom. But in fact, the various momentum and energy conservation principles constrain, vastly reduce the number of degrees of freedom that these scattering amplitudes will depend on. Okay? So the question then you can ask is, how many degrees of freedom, or let us say independent degrees of freedom, are there in two-particle to two-particle scattering? Okay. After accounting for momentum conservation and the conservation of energy. So in order to understand this, let's just imagine that we're in the center of mass frame. Okay. So that's the frame where the two initial particles have equal and opposite momenta. And of course, because the energy of the first particle is the square root of K1 squared plus m squared, the two incoming particles will have equal and opposite momenta and equal energy. And likewise, the final particles will have equal and opposite momenta and equal energy. But by the conservation of energy, the initial energy has to be equal to the final energy. So E1 plus E2 has to be equal to E3 plus E4. E1 is equal to E2. E3 is equal to E4. So energy conservation in the center of mass frame tells us that E1 is equal to E3, which is equal to E2, which is equal to E4. Okay. So the basic picture that we have is that the only actual degrees of freedom that we have are the following. So you imagine that you start out with two particles with momenta k1 and k2 that come together and scatter. So that's the before the scattering process. And in the center of mass frame, there'll be some final momenta k3 and k4. And the only degrees of freedom that we are left with when we consider 2 to 2 scattering are the initial energy E1, or we could call that the initial momentum of one of the particles K1, its absolute value, and the relative angle of the scattering, which we will call theta. So at the end of the day, once we impose momentum and energy conservation, and we use rotational invariance, we are left with 2 degrees of freedom. So I'm ignoring the sort of trivial degrees of freedom where, for example, k1 vector could point in the z direction or the x direction or the y direction, because I can always, by rotation, set k1 to point, say, in the z direction. And likewise, by second rotation, I could take k3 to point to lie in a plane, so say the yz plane, and we're only left with one angle theta, which would be the angle that k3 makes in the yz plane. Okay. So what you're left with are 2 degrees of freedom. And so whenever you study 2 to 2 scattering, the final answer that you get for the scattering amplitude must be expressible in terms of these 2 degrees of freedom, E1 and theta. However, these 2 variables, E1 and theta, are not really the most intelligent choice to use when you want to study 2 to 2 scattering. The reason being that we're studying a Lorentz invariant theory, a special relativistic theory, and so it's more convenient and your answers will look much nicer when we use Lorentz invariant quantities. That is to say, scalars, to parameterize these degrees of freedom in 2 to 2 scattering. So E1, of course, is not a scalar. It's the first component of some 4 vector. And theta is also transforms in non-trivially under rotations, for example. Okay. And in fact, if you look at this formula that I've written here for 2 to 2 scattering, you can easily guess what the appropriate variables to use are. They're just these combinations of momenta that are appearing in the denominator. So these are known as the Mandelstam variables. So S is K1 plus K2. That's the first Mandelstam variable, quantity squared. It's the total, it's related to the total center of mass energy. T will be K1 minus K3 quantity squared, and U will be K1 minus K4 quantity squared. Or if you wish to expand these out using the fact that all of the k's square to 1, square to m squared, this is 2m squared minus 2 K1 dot K2, and similarly, plus, similarly for T and U. And it's a fact that's not so difficult to prove, maybe you'll prove it on the next problem set, that any these parameters E1 and theta can easily be written in terms of these Mandelstam variables. Now, I told you that there were only 2 degrees of freedom, but I wrote down for you 3 variables. So you better not be surprised if I tell you that they're all related. So in particular, if you sum the 3 Mandelstam variables, what do you get? Let's just sum up these expressions here. You get 6m squared plus 2 times k1 dot k2 minus k3 minus k4. But by the conservation of total momentum, this is k1. So you get, minus k1. So by the total conservation of momentum and using the fact that k1 squared is m squared, this is just 4m squared. Okay. So in fact, u is not independent from s and t. And in general, when we talk about 2-to-2 scattering processes, we usually refer to this process where you have the internal momentum k1 plus k2 as S channel. That's the decay and re-emission process. This process, which is the interchange of an intermediate particle as a T channel, and the other one as the U channel. Okay. Good. And in general, these variables are very useful not just for the scattering of 4 identical particles with the same mass, but also for 4 particles of different mass. So in which case, it's easy enough to show that S plus T plus U is equal to the sum of all of the particles of their mass squareds. Yes? Well, yes. So when I talk about these Mandelstam variables, so when I talk about the number of degrees of freedom in 2-to-2 scattering, that's just a statement about the kinematics of 2-to-2 scattering. It doesn't depend on what sort of processes I'm considering. But when you consider the particular 2-to-2 scattering things that I've drawn here, we often give names to these different processes. We call them S channel, T channel, or U channel. Yes. 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 So for example, in a phi to the 4th theory, you would get a diagram that looks like this, that contributes directly to this process at linear order rather than quadratic order in the coupling. Okay. And there's no internal momentum there. Okay. But in some sense, that is not a very interesting process because there's no virtual particle in the interior of this diagram. Okay. I won't say it's not interesting. It's fascinating, but it's not as fascinating. That's a value judgment. I shouldn't make value judgments. The diagram will feel bad. Okay. But yes. Any other? Did I answer your question? I'm not sure if I did. Yes. Mm-hmm. Yes. So you can always use these Mandelstam variables. When you have a theory of spinors or vectors, you'll also have to keep track of other data. In particular, for a vector, you would have to keep track of the polarizations of, say, the photons that you're sending in. But that's something that we'll have to come to when we talk about vectors and spinors and so forth. But as far as the kinematics of the momenta, the Mandelstam variables are all you need. Good. Good question. Okay. Now, it turns out that in the present case, for 4 identical particles, the S, T, and U are not completely free parameters. In particular, S has to be greater than or equal to 2m squared. So that, I guess, can be most easily seen by computing S directly in center of mass frame. and expressing it in terms of the energy E1, and then using the fact that E1 has to be bigger than 2m squared, because m squared is the rest energy of one of these particles, and so E1 has to be bigger than 2m squared. So it turns out that S has to be bigger than 2m squared as well. In fact, maybe that'll be the first problem on your next problem set, showing that for 4 identical particles, S has to be bigger than 2m squared. Okay. So in particular, when I said that we observed the intermediate particle by looking at, for a pole of the scattering amplitude, I was being a little glib, okay? Because our scattering amplitude took the form of 1 over S minus m squared plus 1 over t minus m squared plus 1 over u minus m squared, all times that overall factor. So you can see that that does indeed have a pole at S equals m squared, but you could never actually reach that pole when you have 4 identical particles. Okay. So if the intermediate particle is one of the original particles with mass m squared, then the pole at S equals m squared is unobservable. However, let's imagine the more interesting case where we have a theory with 2 different species of particles. So imagine a theory with 2 different species of particles, phi and chi, and let's say that the phi's are very light and the chi's are very heavy, so that m phi squared is less than m chi squared. In particular, I'll assume that m phi squared is less than 1/2 m chi squared. And we have an interaction where 2 phi particles can join together to create a chi particle. So you have a cubic interaction of this sort. Then that means that you would have, let's say you were studying phi to phi scattering, you would have some process like this, where you have phi's that combine to make a chi that then decays into 2 phi's, plus all the various other channel diagrams. Then this would lead to a scattering amplitude which would look like, well, minus ig squared times 1 over S minus m chi squared plus 1 over t minus m chi squared plus 1 over u minus m chi squared. And this now will have a pole at S equals m chi squared, which is visible. So, in particular, and this is literally what people who study particle physics do, you could study 2-to-2 scattering, where you have 2 incoming particles and 2 external particles, and you could graph the scattering amplitude as a function of energy, and then it'll have a peak at the energy of the internal particle. So typically, if you go to a talk on particle physics and they say we discovered a new particle, they're always looking at a scattering amplitude. They're usually looking at a scattering amplitude and they're showing you a bump. And this is what that bump is. It's the pole when some internal particle becomes on a shell. Okay. So a bump equals new particle. Now, it's not going to be literally a pole, typically, because the internal particles that people usually study are not stable particles, but they're rather unstable particles. And as we'll see a little bit later in this course, when we talk about unstable particles and decays, that will lead not to a pole, but rather to something that's almost a pole, some bump, or what's called a resonance. Yes?
So the that means don't diverge.
When you study 2-to-2 scattering in this process, you will literally get a pole. So you will literally get a divergence. But in realistic scattering processes, so for example, when people study the Higgs, when people are looking for the Higgs by itself is very short-lived. Okay, and so that turns out to lead to a scattering amplitude which does not have a pole, but which has a bump. And essentially the width of that bump is the lifetime of the unstable particle. Yeah. So we'll get to the subject in more detail of resonances and particle lifetimes and stuff like that. But this is you can see already just the basic strategy that you look for peaks in these scattering amplitudes, and that leads you, there'll be peaks when you have particles. Yes?
I'm not sure I understand. Isn't chi unstable because here it is decaying back into 2 pi particles?
Indeed. Yes, that's why I drew it as a bump. Okay. Okay, yeah. So, yeah, let's table this. Yeah, okay. No, that's a good point. Let's wait until we get to our discussion of decay processes, and then we'll understand this in a bit more detail. Yeah. No, that's a good point. Good. Yeah. Other questions? Yes. Sure. You could also study decay processes. We just have one particle decaying into others. Okay. But typically, the sort of situation that we're in is one where the typical situation that we're in is where we have some sort of light particles like these phi particles that are easy to produce and easy to study. And then we have other particles that are difficult to see directly, and so you can only see them through their decay products. Okay? And this is the sort of simplest situation where that might happen. Good. Other questions? Yes. Okay, well, I mean, of course you need, yes, okay. You need to study all sorts of different scattering processes and understand, the scattering processes involving all sorts of different internal particles in order to be able to distinguish between them. And so, for example, you can see that you can read off from this sort of picture the mass of the internal state, the mass of the exchange particle. And so the first thing you would do is check whether the mass of the Higgs particle agrees with the mass of whatever you think, maybe it should be identified. You might be seeing. And if the masses don't agree, then, well, that's a pretty good hint that you're looking at something new. And then there are other sorts of, checks that one can make. So, the first thing I would say is that the mass of a anti-top pair would be much bigger than the mass of the Higgs by some several hundred GeV. So, that would immediately rule out that. But, in general, those are the sorts of things you might have to worry about. The top would have very specific interactions with the other sorts of particles. So, that's the sort of thing that you would have to nail down by looking at the entire theory. But that is something that people worry about. For example, is the Higgs that people see really, is it the Higgs of the Standard Model? Is it the Higgs of some other theory? Is there more than one Higgs? If there is, which one are we observing? This is all sorts of things that people worry about. Good. Other questions? Okay. Okay. So there's one final point I want to make about the connection with experimental observables. So in particular, so far, we've computed scattering amplitudes But quantum mechanical amplitudes are, of course, not what we actually observe in some sort of experiment. So what is it that we would observe in some sort of particle physics experiment? Okay. So let's consider a beam of particles. And typically, the way that you would parameterize this beam is by talking about the flux of particles. And the flux of particles, usually denoted phi, is the number of particles per unit volume in the beam. So if the beam occupies some volume, it would be the number of particles per unit volume times the velocity of the particles. And what this tells you is really the number of particles passing through some particular area per unit time. So passing through some area per unit time. So the picture you would have in mind is you have some beam of particles, and you have some, say, target here, and you would describe the beam by some flux. And let's first just imagine the simplest case where you have a fixed hard target. Okay. So for a fixed target that is completely, just fixed in space, then what would you observe? You would observe the cross-sectional area of the target. In particular, let's say you had some beam of particles that are incident, say, on some sphere, then you would be left with some sort of shadow here in the beam of particles. And that shadow would tell you the cross-sectional area of the sphere off which these particles are scattering. So when we talk about particle physics experiments, we usually like to characterize the results of these experiments in terms of this cross-sectional area. Okay? So in general, we define the cross-section of a scattering process as follows. We define it as the total number of particles scattered per unit flux per unit time. Okay. And you can see flux has units of particles per unit area per unit time. So this is proportional to area. So this has dimensions of area. And indeed, for the case of some flux of particles that are just scattering off of some fixed hard target, then this is literally the cross-sectional area of the target. Okay. So for example, this would be pi r squared for scattering from a hard sphere. So typically, when we study some scattering process, we don't just look at the total cross-section, but we actually observe the momenta of the final state. We observe the momenta of the outgoing particles. Or if they're, say, photons, we might also observe their polarizations or something like that. And so typically, what we're interested in doing when we study a scattering process is we fix the initial momenta and consider the number of particles scattered as a function of the final momenta. So that means that we're interested not so much in the total scattering cross-section, but what is known as the differential scattering cross-section, as a function of the initial and final momenta. So, for example, if you have, say, m final particles, then you might be interested in the differential cross-section d sigma by d omega 1 up to d omega m, where omega I denotes the solid angle into which the ith particle will scatter. So here, omega would denote the two angles theta and phi on the two-sphere out at infinity into which one of these particles will scatter. And typically, this cross-section is constrained by kinematics in the sense that the final angles into which these particles will scatter is constrained by kinematics. Okay? So for example, for 2-to-2 scattering in the center of mass frame, we really don't need to consider d sigma by d omega 1 and d omega 2, where you have the solid angles of all of the different possible final states of the particle. But really, we're only interested in d sigma by d theta, where theta is this angle here that we considered in 2-to-2 scattering. That tells us the relative angle of the scattering relative to the initial state. Okay. So this is the relative angle of the initial and final scattering. So the question then is, how do we go ahead and compute the scattering cross-section from things that we already know? So how do we compute sigma, or the differential cross-section d sigma, from the matrix element, or the S matrix element, that tells you about the scattering, the quantum mechanical scattering amplitude from some final state into some initial state? So roughly speaking, of course, this scattering cross-section will be some scattering probability that's going to be the absolute value squared of this scattering amplitude, along with some kinematic factors that, well, it's important to get right once and then not really worry about too much in the future. So in the last sort of maybe 5 or 10 minutes, what I'd like to do is just work out the kinematics that allows us to relate these scattering cross-sections to these S matrix elements, and then we can just dispense with that and continue to work with these scattering amplitudes, the S matrix elements, for the rest of this course. Maybe before I do so, I should pause and see if there are any questions.
Are you in the specific frame? In the single mass frame?
Well, so what I'm going to do is work in, I'll write down a formula that works in any frame. Okay. And at the end of the day, what will end up with is a formula for the differential cross-section expressed in terms of variables that you could then use in whatever frame you like. Okay. So for example, one could then work in center of mass frame, and then theta would be the important variable. Or you could work in some other frame where you have scattering off of some target. So let's say that one of the initial particles is fixed and the other is not, and then you would have some other kinematic variable that you would want to use. So for example, sometimes in classical mechanics or quantum mechanics, people will compute these differential cross-sections for Rutherford scattering. Have you guys ever done that? Okay, another great, you did do that. Yes? In quantum 2 you did. Okay, good. Okay. So the first thing to notice is that the total probability that some particle will decay, some particles will scatter. So that's the number of scattered particles over the total number of particles in some beam is just this overlap squared along with some normalization factors to take into account the fact that we may or may not be normalizing these initial and final states to have unit norm. Okay. And what we really want to do is consider this as a function of final momenta. And so the differential probability is going to be, so what we really mean is that the differential so this probability that I've written here is a function of some of the initial and final momenta which are fixed. And what we really want to do is understand the probability as a function of those final momenta. So we want to talk about a differential probability, dp, which is given by that expression above, times some appropriate measure factors, so that I'll call d pi, where d pi is just a measure on the state of final particles. So so that measure factor is just d3p. And the only subtlety is that what I would like to do is I would like to make sure that this measure factor is appropriately normalized so that the integral over all of the final momenta of dp is over all of the final momenta is equal to 1. So what that means is that what I need to do is think about working in a space of finite volume, say a sphere of very large volume, and then include a factor of the volume here. Okay. 1 over the volume here. Actually, the volume here. Okay. So what is the flux of particles? So here we just think about a single particle. And if you have one particle, remember that the flux is defined as the number of particles that in a beam per unit volume times the velocity of the beam. So that means that if you have some incoming particles, say in center of mass frame, it would be velocity over the volume of space, or so that's in center of mass frame, or more generally in non-center of mass frame, you'll have the difference between the two incoming particles if we're studying some initial state with 2 particles. So our goal then is to calculate the differential cross-section, which will be 1 over the total time that you're running the experiment, the total time interval you're considering, times the flux times the differential probability So I see that I'm actually out of time, and I see that although I've been rushing a little bit, it's going to take me more than the 5 minutes that you might put up with in order for me to derive the differential cross-section. So maybe what I should do is just pause here in our derivation and pick it up at the beginning of class next time. So at the end of the day, what we're going to do is, well, I mean, would you guys prefer that I do this at the beginning of class, or do you want to take 10 minutes to do it now and then move on to more interesting things next class? Maybe I should take my time and not rush through this. I mean, it's really, it's about another page. So rather than rushing through this, I'll just pause here and finish the differential cross-section next class. Okay. Good. Oh, should I? I had thought about scheduling a makeup. Yeah, I had never got around to thinking about that. Should we schedule a makeup? Yeah, we should schedule a makeup class. That would be nice. What was the day that worked for people? Was it Fridays? Was that the day that worked for everyone? Okay. So let me go about figuring out how we would schedule that. Let me find a room. So we will not have class tomorrow. Okay. But maybe some other Friday we will have class. That'll be exciting. Okay. Good. Okay. I will see you all on Tuesday then. Thank you.